class of science physics, and I'm Mrs. Wolfen, and today we're gonna do some plug and chug, even more practice for chapter 7 stuff. A couple of things I want to review with you, the different types of problems we have on this sheet. We have some momentum problems, we have some impulse problems, and we have some that use the smush formula, as I like to call it, where you have the change in momentum equals the formula for impulse. Then we also have some collision problems when you have two objects that are separated before collide and then have two separate objects each going in at different velocities after. That's one type of collision, that's an elastic collision, and then we also have inelastic collision, which is the two objects are separated before, but because they stick together during the collision, you have to add their masses. They now act as one object with one velocity. Okay, let's dig into this. What is the momentum of a 5 kilogram shot put? So mass equals 5 kilograms. See if I can adjust my camera so you can see while I'm writing here. Might be a little bit better. Yeah. And it's rolling at a velocity of 4.5 meters per second south. And we're interested in the momentum, lowercase p. So this is our formula because it's the only one that has all three of those things in it, and just those three things. So let's substitute into the formula. Put my mask off here, sound a little bit better. So we got momentum equals 5 times 4.5. And when we do the math on that,
any students who do pool testing,
this is our life these days.
1 through 13 who has not gone to the lobby, please go. That's any student who has not gone to the lobby, does pool testing 1 through 13. Please report to the lobby.
Yep, there you go. So when you multiply these two together, you get 22.5 kilograms meters per second, and because momentum is a vector quantity, we need a direction, and the only direction we have is south. Okay, the next problem, if the shot, and we're talking about the same shot put, rolls into a pile of hay and stops in 2 seconds, calculate the average force. We're looking for a force. The shot put exerts on the hay. The shot put has a mass, and this is the same mass as in the previous problem, 5 kilograms, and it's rolling with a velocity of 4.5 meters per second south. So this is one that we have to use the smush formula. So we have mv equals ft. So we have 5 times 4.5 equals force times 2. So simplifying this side, we have 22.5 equals 2f. We're going to divide both sides by 2. So we end up with 11.25, and we're looking for a force, so that's going to be newtons, and we know that we need a direction on that. So it's going to be the direction of the velocity, which is going to be south. The next problem is not any math that you have to do. It's just little thinking. So what's the average force? So we just calculated the force the shot exerts on the hay. Now we need to figure out what the hay exerts on the shot put. And you remember from chapter 6 where Newton's third law says that for every action, the force of the shot on the hay, there's an equal and opposite reaction. The hay exerts a force on the shot. So the number is going to be exactly the same. The unit is going to be the same, but instead of being south, it's going to be north because it's equal in magnitude, opposite in direction. Okay, let me see if I can slide this down here just a wee bit so you can see the very last problem on this page. What's the momentum? So we're looking for momentum of a 0.25 kilogram black cat chickadee. So that's the mass. That slides with a velocity of 3.2 meters per second east. across mostly frozen Lake George. So we need to use the momentum formula. So momentum equals 0.25 times 3.2, and a quarter of 3.2, I believe, is 0.8 meters per second, and because velocity, nope, momentum is wrong unit. Woo, almost made a terrible mistake there. Momentum is kilograms meters per second, and we need a direction, so it's going to be east. Okay, so that takes care of the first page. Let me slide this out. Your world is going crazy here because I'm moving stuff around. Okay, so the sliding chickadee from the previous problem skids onto a rough surface and stops in 4 seconds. Calculate the force of friction the chickadee encounters. The chickadee has a mass of 0.25 kilograms, and it's sliding eastward at 3.2 meters per second east. So again, we're going to have to use the smush formula, mv equals ft. So we have 0.25 times, let me do a little auto. There we go. Might be a little bit better to see. 0.25 times the velocity, which is 3.2, equals force times 4. So we figured out in the last problem that a quarter of 3.2 is 0.8 equals 4 times the force. We're going to divide both sides by 4. So our answer down here is 0.2. And we're looking for a force, so that would be newtons. And what direction is our force going to be in? Well, the only direction we have is east, so that must be the direction of the force. Number 3, we need to find the impulse, which is J, that occurs on an average leftward force of 6.2 newtons left on a bunch of plantains, which are kind of like bananas, for a time of 1.5 seconds. So J equals Ft, impulse equals force times time. It's one of your formulas on the first page of this thing. So J equals 6.2 times 1.5. So when we multiply those together, we end up with 9.3, and we're looking for an impulse, so that unit is a newton second. And because impulse is also a vector quantity, we need a direction, and that's going to be left. What is the next question says, what is the change in momentum? Well, since it says on the first page, J equals delta P is the change in momentum, and that is the same as the impulse. So whatever the impulse is, that's what the change in momentum is, but we got to use a different unit. So it's kilograms meters per second left, because we're looking for a momentum, not an impulse. Okay. Next problem. If the mass of the plantain was initially 2 kilograms and the bunch of plantain are initially at rest, calculate its final speed or velocity. Then we have a force of 6.2 newtons left, and we have a time of 1.5 seconds. So mv, the smush formula, comes into play again. So we have 2 times v, because that's what we're looking for, equals 6.2 times 1.5. So 2v equals 9.3. Multiplying those two numbers together, we're going to divide both sides by 2 to get the v by itself, and we find out that the answer is 4.65, and we're looking for a speed, which is meters per second. Because it asks for a speed and not a velocity, then we don't need to put a direction on it. Okay, So that takes care of the impulse and momentum problems. The next problem that we have to do is a little bit more complicated because it's a collision problem. We're going to have to do the before and after deal with this. So first we have a 2 kilogram blob of peanut brittle. So mass of the peanut brittle is 2 kilograms. It's moving to the right. Velocity of the peanut brittle is 1.5 meters per second right. It slams into a blob, 2 kilogram blob of taffy, so mass of the taffy is 2 kilograms. And the taffy is initially at rest, so the velocity of the taffy is going to be 0. So the masses are not going to change after, but they're going to get stuck together, so instead of having these two individual velocities, we're going to have a velocity of both, and that's what we need to find. So the two things are separated initially, so we'll make them separated initially, and we'll calculate the momentum of them, times, velocity of the taffy equals the masses of them added together because they're acting as one thing times the velocity of both. Okay, so let's plug in. This is why it's really important to write down what you know so that you know where to plug things in. So we have 2 times 1.5 plus 2 times 0 equals 2 plus 2, which are the two masses added together, times the velocity of both. Now, because this is 0, we can just ignore that. So 1.5 times 2 is 3 equals 2 plus 2 is 4 times the velocity of both. So we're going to divide both sides by 4 to get the velocity by itself. So the velocity is 0.75 meters per second, and that's going to be to the right. Okay, whew, that was a lot of stuff going on there. Okay, next problem. Calculate the velocity of the two blobs if the one at rest was at 4 kilograms. Use the data from part A to calculate. So we know that the initial blob of peanut butter was 2 kilograms. We know that the velocity of the peanut brittle is 1.5 meters per second right. Now this part says that the one at rest has a mass of 4 kilograms, but its velocity is still going to be 0. So those are going to be exactly the same, but we're looking for the velocity of both, just like we did in the last one. Same formula. Peanut butter plus the mass of the taffy times the velocity of the taffy is going to give us the combined masses times the velocity. So we have 2 times 1.5 plus 4 times 0 equals 2 plus 4 times the velocity of them both. So we got 3, and we can ignore that because it's 0, equals 6 times the velocity. We're going to divide both sides by 6 to get the velocity by itself. So the velocity is 0.5 meters per second and to the right. Next one seems like it's a really, really long problem. Let me raise my camera a little bit so we can get the tail end of that in there. Okay, so we got an unconscious flamingo sitting in a pushcart that's traveling down Bigelow Hill in Skowhegan. It's going 7 meters per second northeast. So the velocity of the flamingo is 7 meters per second northeast. The mass of the flamingo in the cart are 200 kilograms. The flamingo and cart hit a rock and veer off the road, running into a bale of hay. So the mass of the hay is going to be 500 kilograms. That is stationary. So the velocity of the hay is going to be 0. The cart and his flamingo passenger get hooked on a bale of hay and they move off together. So this is going to be one of those inelastic collisions where the two things are stuck together. So this is going to be the same, but we're not going to look for an individual velocity. We're going to do the velocity of both is what we're looking for. So same formula that we've been using. Oops, this is a F right here. Velocity of the flamingo plus the mass of the hay times the velocity of the hay. This is all before. And that's equal the after, which the two things are stuck together. The mass of the flamingo plus the mass of the hay times the velocity of both. All right, so let's plug in here. So we have 200 times 7 equals 500, plus 500 times 0 equals 200 plus 500 times the velocity of both. Okay, so this we can ignore. 7 times 200 is 1400 equals 200 plus 500 is 700 times the velocity of both. We're going to divide both sides by 700. And lo and behold, after all of that business, the velocity is 2 meters per second, and they're going to the northeast. Okay, woo, that was a lot. The next one is a little bit more difficult because it's one of those that they don't stick together, and we really need to pay attention to the direction on the velocities for these ones that don't stick together. So you got a chocolate bar is sliding to the left with a velocity, so mass of the chocolate, velocity of the chocolate is 2 meters per second left. The bar has a mass of 0.3 kilograms. Small dish of peanut butter is sliding to the right with a velocity of 4. So we have velocity of the peanut butter is going to be 4 meters per second right. Now here's the problem. We need to make sure we know which direction is positive and which one is negative. I'm going to say the positive direction is right and the negative direction is left. Doesn't matter which way around it goes, but I usually write it right there so that I know when I get to the end and I have a positive number that the direction is going to be right. The dish of peanut butter has a mass of 0.9 kilograms. This is all before. And then the after. The chocolate and peanut butter collide in an elastic collision. The chocolate moves off, so it's going to be the same mass for the chocolate, but the velocity of the chocolate is it's moving right at a velocity of 1 meter per second. So it's going right now, which we're going to make positive. It was going left before, so we have to make that one negative, and that's the tricksiness of these problems. So we're looking for the velocity of the peanut butter after. So we have mass of the chocolate, velocity of the chocolate, plus the mass of the peanut butter, velocity of the peanut butter. This is the before stuff. And the after stuff is going to be over here. And it's going to look exactly the same because they're not hooked together. So we have 0.3 is the mass of the peanut butter times -2. And that negative is really important because it shows that it's going in the opposite direction of something. Plus 0.9 times 4 equals the same mass. The chocolate has the same mass, but now instead of going 2 meters per second left, now it's going 1 meter per second right, plus the mass of the chocolate again times the velocity, not the mass of the chocolate, the mass of the peanut butter plus times the velocity of the peanut butter. So let's simplify this side. So we got 0.3 times 2 is -0.6 plus 0.9 times 4, which is 3.6, equals 0.3 plus 0.9 times the velocity of the peanut butter. Simplify this a little bit more. 3.6 minus 0.6 is 3 equals 0.3 plus 0.9 times the velocity of the peanut butter. We're going to subtract 0.3 from each side to give us 2.7 equals 0.9 times the velocity of the peanut butter. Now we're going to divide by 0.9 both sides. Oh, we're running out of room here. So it's a good thing because we got down to our answer, and the answer is 2.7 divided by 0.9, which happens to be 3 meters per second. And because it's a positive number, what direction is positive? We set up here, it's going to be to the right. Okay. I think we got one more problem. We'll get this one done, and then we'll be on our way. So, Tawanda the turtle is sliding at 0.5 meters per second to the right. So velocity of Tawanda is 0.5 meters per second right. Across Mrs. Bolden's room, she has a mass of Tawanda is 1.2 kilograms. She runs into a stationary wad of chewing gum left by one of Mrs. Bolden's students. So mass of the gum and velocity of the gum. We know the velocity of the gum is going to be 0 because it's stationary. The wad of chewing gum has a mass of 0.1 kilograms. This is before. And because the gum gets stuck to Tawanda, the after is going to be very similar. But we're looking for the velocity of both of them together because the masses are going to stay the same, but we don't care about the velocities after because they're both going to be together. So we have the mass of Tawanda times the velocity of Tawanda plus the mass of the gum times the velocity of the gum equals, because they're stuck together, mass of Tawanda plus mass of the gum times the velocity of both. So we have 1.2 times 0.5 plus 0.1 times 0 equals the mass of Tawanda, which is 1.2, plus the mass of the gum, which is 0.1, times the velocity of both. So this we can forget about. Half of 1.2 is 0.6 equals, combining these two terms, it's 1.3 times the velocity of both. All of this shrunk down to just this. So we're going to divide by 1.3, both sides by 1.3. And when we do that, we get 0.461. And that the 1 tells us we're going to leave the 6 just as it is, 0.46. And we're looking for the velocity, which is meters per second. And what direction is it going to be going in? Well, it's going to be moving to the right. Whew! That was a lot. I hope you stuck through all of that. Thanks for joining me. Have a great day.